Welcome to solverfy.
Okay, in this problem, we're taking a look at a proton inside of a nucleus, which has an extremely small radius, 5 times 10 to the negative 15 meters. So if we take this radius to be our uncertainty in position, we have a corresponding uncertainty in momentum, which we're asked to find. And from there, we're asked, what would the potential energy of the strong nuclear force be in order to keep this proton inside the nucleus if it has this expected fluctuation in momentum. So the equations we'll be using for this problem are, perhaps not surprisingly, the Heisenberg uncertainty principle, which relates uncertainty in position to uncertainty in momentum, puts a minimum bound on it. And we have the kinetic energy, which we were asked to use a relativistic expression for this particular situation. This is it. For constants, we have Planck's constant, reduced Planck's constant, h bar, which is simply h over 2 pi, and the speed of light. So let's jump into it. So to start, we can simply apply the uncertainty principle. We have everything. By assuming that the radius of the nucleus is our delta x, we can find a corresponding delta px, or uncertainty in momentum. Plugging in h bar and our delta x of 5 times 10 to the negative 15 meters, we end up with a momentum fluctuation of 2.1 times 10 to the negative 20 kilograms meters per second. So this doesn't seem like much, but for a subatomic particle, something so small, to have this momentum, it's significant. So let's box that. So now that we can take this as a momentum, we can now apply our kinetic energy formula. K equals root PC squared plus MC squared squared. Plugging in P and speed of light and mass of a proton, we will have a result of, oh, I'm missing one thing. Since we're trying to find the potential energy, we have to be very careful. Kinetic energy plus potential energy equals total energy. So we have to subtract an MC squared, a rest energy, from this particle to do our full energy accounting. So once this is done, we will have a result of 3.07 times 10 to the negative 12 joules. And since we're interested in a result in electron volts, we can use the fact that 1.6 times 10 to the negative 19 joules is 1 electron volt. So we will get to a result of 0.82 mega electron volts, MeVs. So as mentioned, the energy of the binding energy of electrons around the atomic nucleus is on the order of tens of EVs. This is millions of EVs, or a little less than a million EVs. So you see that the potential energy of the nucleus in order to bind the protons to it has to be some extremely large number. And the reason is because momentum fluctuations will create large kinetic energy fluctuations, which could be large enough for a nucleus to escape if the binding energy was not big enough. So the reason why this momentum fluctuates so much and the nuclei want to escape so badly is because the delta x is so small. So by confining these protons to the nucleus to such a small scale, it requires a stronger and stronger force because they want to repel by the uncertainty principle. So that's the main results.